Hi, class. So, uh, based on what we talked about last week, many of you had some questions about sort of statistical significance and distributions. So I thought I would be good to have a supplementary lecture to just go over some of the important high-level facts and provide a little bit of extra background around probability distribution, significant testing, and ultimately tell you where we're going to go. So the big things that I want you to take away from this lecture and where we're headed and why this is relevant for the rest of the course is you need to understand a little bit about probability distributions in order to conduct significance testing. And meaning significance testing is often used for analyzing your data and drawing inference or making comparisons. So typically you'd want to use significance testing to sort of say if your sample statistics are different from some sort of norm or benchmark value, or if one treatment were more effective than another. The other reason why we just want to have an understanding of these probability distributions is we also use significance testing for the interpretation of linear and logistic regression coefficients. We aren't going to get to that in this video, but linear regression and logistic regression are sort of the endpoint for this course. And if you can understand how to run linear models, then I will consider this course a success. So just going back to sort of the high level interpretation of data, that we have roughly 4 different buckets we can group data into. So we have continuous data. Those are numbers that have a range, and that, so for something like temperature, you have values from basically anywhere between 0 degrees Kelvin and hundreds of thousands of degrees, if not higher. And almost any point in between there can be represented as a real value and could potentially occur. Then you have things like discrete numerical data. Those are things like say the results of rolling a die or flipping a coin, that there are a fixed number of values that can occur, and we can count them pretty easily. The other types of data that we will work with are what I refer to as categorical. There's nominal, so that could be something like, say, a patient's blood type, where there isn't necessarily a clear ordering of what should come before or after. And then we have something that could be called ordinal, which means that there's a natural and logical sequence that you might want to assign to it. So something like shirt size, which could be grouped into small, medium, large, and extra large. And while they might not necessarily correspond to a numerical value, you might want to treat one as larger than the other. So just recapping real quick what we know about probability distributions. The things that I want you to take away are that each probability associated with a distribution must be somewhere between 0 and 1, and that the probabilities must total to 1. What this basically means is that when you are looking at your data, or when you are trying to understand how your sample is being generated, you need to know that you need to understand that in order for your sample data to be a probability distribution, is that each potential outcome you're looking at needs to occur with probability 0 to 1, and that the sum total of probabilities must be equal to 1. Typically, the way people do this is that they sort of normalize their sample data. But we don't need to get too far into the weeds on that. What I do want to show you, though, is an example of what a discrete distribution looks like. So, and there are many families of discrete distributions that have their purposes, and if you were to take another formal stats class, you might see this come up a fair bit. But we're not going to get into all of the applications and uses of these distributions. I just wanted to throw them out there so they seem a little more familiar if they come up in your reading or subsequent courses. And again, what a discrete distribution is just is that it has finitely many defined outcomes. So things like dice rolls or coin flips or even grades. And it has associated with it, each potential outcome in the distribution has mass, meaning that there's an associated probability value associated with it. So for instance, if I were to throw a die, that the probability of getting a particular side comes up with 1/6, or if I were to flip a coin, the probability of getting a head is approximately 1/2. And what I show below here is an example of a probability distribution of the sum of two dies. And what you sort of see is that even though a particular die roll is what we'd call uniform, that when we start to make operations like compute the sum of two dies, that it starts to look a little bit more normal or more bell curve shaped. And visually we can see this, that part of it is just that when we roll two dies, that there are more possible ways to get a 7 than there are to say get a 2 or a 12. That's all I want you to know about discrete distributions. Again, we aren't going to be using these techniques too formally, but it's helpful to have a little bit of an intuition of what's going on. Then we have something called continuous distributions, and unlike discrete distributions where probability has mass, in a continuous distribution, a probability has density. What that basically means is that if I were to pick any point in my distribution, that the associated probability of picking exactly that point is going to be 0. I know that sounds a bit confusing, but we know that because it's a probability distribution, that it has to sum to 1. How can it be that if we were to pick any particular point, it's equal to 0? Now, without getting into the calculus of it all, what we do is we actually look in between values to approximate the associated probability between a distribution. And one of the things I want to highlight here is that the definition of discrete and continuous distributions are actually a little bit fuzzy in and of themselves, is that as you start to use more and more granular bin widths or approximations or gain more precise measurement, your data just starts to look more continuous. So in fact, this is all the same underlying data, just as represented with slightly different bins. And again, what you can do is, without getting into the calculus of all this, you can sort of approximate the associated probability of an event by counting how tall this bin is and then dividing through by the sum of all of these other bin heights. And again, what typically we do is we figure out our research question of interest. So for instance, what percentage of individuals have heights between 180 and 185 centimeters? And then we use a computer or a numerical methods technique to look at the area under this curve. And of course, when we are talking about continuous distributions, the most popular and the most useful one that comes to mind is always going to be the normal distribution. And the things that I really want you to take away from this normal distribution is that it's symmetric, meaning that its associated density function is the same as you move to the left of its mean as to the right of its mean. And what we also know is that there are certain useful features to understand how likely, if you were to pick a random number from the normal distribution, it's going to fall into certain regions. So for instance, we know that 68% of all observations will normally fall within plus or minus 1 standard deviation. And as we increase the sort of width of how many standard deviations we're willing to look across, that we cover more and more of the possible distributions. And that as we use wider and wider bins, we cover more data, but it asymptotically decreases. So for instance, when we use 2 standard deviations, we cover 95% of the data. And when we use 3, we only cover an additional 4.7%. So why does this matter? Well, often what we like to say when we are doing statistical analyses is we want to compute things into something called a z-statistic. And what we do when we do that is we go through and we take a sample value, we subtract off the mean of the associated distribution and divide through by our standard deviation. And what that does is it returns what we call a normalized score. And what you can then do is, once your data is normalized, you can, and what people used to do was they would go through statistical tables where someone had already calculated what the area was under these curves once you normalized this type of distribution. And you could look up how much probability was, say, to the left of this line. So for instance, in this example, it would cover roughly a little more than 70%. And again, these are just rough numbers, and thankfully now SPSS will do this all for you. But I just wanted to show this type of example of what this work looked like prior to statistical softwares. And just to run you through a sample problem, here we are trying to normalize SAT scores. And what we are told is we know that the associated mean is 1500. We have an associated example we're testing where we want to compute that in terms of the z-score. And we were also given a standard deviation. So what we do is we go through, we subtract off the mean, we divide through by our standard deviation, and that returns our z-score of 0.43. And so the probability associated with getting a score greater than 1630 corresponds to this blue shaded region. And what we can then do is we can go look this up in a statistical table. And the other thing that I want to highlight that's useful to keep in mind is one of the other properties of probability distributions is that, again, they sum to 1. So sometimes when you're working with a probability distribution, it might be easier. You might not necessarily have access to say the left-hand side or the right-hand side, but because we know that a probability distribution sums to 1, we can often, if we're given one piece of information, we can also figure out the other due to this joint feature. And this is really helpful, particularly in cases where our probability distributions aren't symmetric like the normal. So the other thing I want to convey is that typically when we are doing statistical analysis, we want to convey information with a certain level of precision. And one of the ways we can increase our precision is by increasing our sampling. And again, the formulas for this will vary depending on the context and what type of analysis you're doing. But the primary takeaway I want you to have is that as you increase your sample size, that your associated standard errors decrease, meaning that even if your data is still as noisy is still as noisy as it would be under other circumstances. The fact that you've taken a larger sample means you can be slightly more confident or use smaller error bands when describing your data. And the way individuals often describe their data is that they use something called confidence intervals. And what a confidence interval is you generate your sample statistics, say your sample average, and then you wanted to express your uncertainty around that number. And what you would do is you would add or subtract the associated standard errors to convey the uncertainty surrounding your point estimate. Apologies for that. And so again, going back to that normal curve, if we were to use 2 standard errors, we would roughly cover 95% of the data. And if we were to use a slightly larger amount of, say, 2.5, we would cover almost 99% of the data. And you choose your confidence interval length to communicate your uncertainty, and you choose the percentage typically based on the level of statistical significance that you're looking at. The big sort of takeaway when you're reading papers or looking for effect sizes is I tend to look at a confidence interval and see whether or not it contains 0. And we'll look at that a little bit more in the statistical analyses we're going to do in the ESS exercise. And the other thing I want to throw out here is that there are a lot of assumptions going into the normality of your data, as well as how you were doing your sampling. I think this is beyond the scope of the course, but it's something to keep in mind. And we now have sort of a working definition of a confidence interval and a standard error. And what often you as researchers are going to do is engage in something called hypothesis testing. And what a hypothesis testing is a process for assessing how likely a certain statistical claim is. And what we often think of when we're doing statistical analyses is we think in the context of 2 competing hypotheses. The first of which is we call them null. And that basically means that we are assuming that our prior hypothesis typically that our null value is equal to 0, that, for instance, a treatment was ineffective, or that our population or our data that we sampled was no different than the true underlying population. And then we go through and we calculate that assumption using our z-score method, and we generate our confidence intervals and we check whether or not 0 is in it. And if 0 is in our confidence interval, we fail to reject, meaning that we can fail to, we have no reason to sort of accept our alternative hypothesis, nor, actually this is really tricky language. And the way this is taught in statistical courses, they really drill this into you. So I'm just going to say an informal interpretation. If you have high p-values, you have little reason to reject the null, meaning that there's not substantial evidence that your alternative hypothesis is true. And to build on this, there are a few different types of statistical tests that I want to go over. There are these things called one-sided test, and that would be when your alternative hypothesis is that your sample mean is significantly different in a particular direction. So for instance, that you might be interested in whether or not a patient's fever is greater than a certain value. So if a patient's fever is, say, greater than 103 degrees, then you might want to engage a certain protocol. And what you could do in a case like that is you do statistical sampling and you do a one-sided test, and what you get is something that looks like this probability. And then there are these things called two-sided tests, where you're assessing how likely that your value is just something different than the underlying population mean. And then what you would want to do is not just count the probability in, say, to the right of a particular value, you'd also want to incorporate the left-hand side. Now, the examples I'm running through are just assuming a z-score, but they largely generalize to other statistical distributions. So the things that I want you to take away from this are that this is what the generalized approach looks like. In practice, actually, what you end up using is something called a t-distribution. And we use a t-distribution for a couple of reasons. One of which is often we don't know the true population variance. So we actually have to use a sample estimate of the population variance because we can't necessarily, we have to rely on our own sampling method. And again, the way that people used to do this in olden times, meaning when I went to college, is that we had pre-made statistical tables, and what we could do is we could look up associated sort of normalized values and what percentage of the data is associated with a particular t-statistic. So for instance, in this case, if we were to have, say, 18 observations, the probability that we'd get something below negative 2.1 standard deviations or standard errors is this amount. That's our associated t-statistic, and the associated probability of being less than, say, less than this value is approximately 0.25. Again, you don't need to worry about this. SPSS is going to do it all for you, but just to provide a little bit more context of how this was done in the past. The other statistical test that you're going to be using a lot is not just comparing, say, one mean, but possibly multiple means. And for that, you use something called an F-test. And again, we aren't going to get too much into the mathematics of that, but what I want you to understand about the F-test and its associated distribution is that unlike, say, our normal distribution, is it's not symmetric and it's also skewed. And again, typically you'd want to use an F-test when you're comparing multiple means, or if you're, and this holds more weight and more importance when we get to linear regression, where there are going to be lots of coefficients that we're going to be using all at once. The other statistical test that I want to introduce you to is something called a chi-squared test. And what it's used for is to check the independence of categorical variables. Specifically, what that means is you want to see if there's a relationship between two categorical variables. So for instance, one thing you can imagine is that shirt size might be related to high blood pressure. And what you could do to sort of test that is assume that shirt size and blood pressure were completely independent, meaning that the probability of having one did not influence the probability of the other in any way. And that is sort of our null hypothesis, that in most cases when we're doing a chi-squared test, is that these data are independent, meaning that they don't affect one another. So what we can do is we can generate how likely these events were to occur, assuming independence, and then compare that to the actual co-occurrence. And I'm not going to get into the exact calculation right here, but what you do is you look at the cumulative difference across all of these individual cells. And that will, and then you will again go to one of those statistical tables, or rather let SPSS do it for you, and then that will inform you whether or not it's statistically significant or not. Well, that is the end of sort of the lecture component, and let's get started on some more analysis in SPSS. Thank you.